Okay, so how is everyone today? Good? All right, so this is Math 2370, right? Okay, good. So I'm the instructor, Dr. Brady McCary. So just some brief notes about the way that the course is run is that when we're doing lecture, I'm going to do it on these pages here. And I'll always start out by writing the date. Today is the 21st. So after the lecture's over, I scan these pages and I'll post them and you can download them, so that's nice. In addition to that, I'm recording this section, so this is gonna, it's on video, and I'll post that to YouTube, so you can look at that too. That's neat. But please don't take that as license not to come to lecture for a couple reasons. Okay, one just purely teaching reason is that the more engaged you are in this activity, the more likely it is that you're going to retain what we've discussed. But in addition to that, there's going to be homeworks that are due in lecture, and I won't accept them at any other time. And there'll be in-class quizzes, and it won't be permissible for you to take them at any other time. So, you might as well come. Any questions about that? All right. So, how to get in contact with me? The best way to get in contact with me is by email. This is my email address. So, in case you didn't understand this yet, when you're at UTD and you're taking a class, you have a formalized relationship with your instructors. So, like, we have like an instructor-student relationship. And what that means, among other things, is that when we communicate over email, you have to send your messages to me from your UTD email and to my UTD email. And I can appreciate that everyone and their pets and everyone has a Gmail account or whatever. Okay, but you can't send me an email from your Gmail account. It'll literally just be deleted and I'll never see it. Okay. The reason for that, in the end, is basically, your physician, your medical doctor, they've got rules about your medical records. Like, I can't just walk up to some doctor's office and say, "Hey, I'd like to look at your medical records." They're going to say, "No, you need to leave." That's all that they would say. Your instructors have a completely analogous rule. In the case of medical doctors, the laws are called Hipaa, and in the case of your academic records, it's called FERPA. And one of the consequences of that is that, if your mother or your cousin or someone says, "Hey," to me, "Hey, how's Joey doing in the class?" Basically, all that I'm allowed to say is I neither confirm nor deny that Joey exists, and that's all that I can say. So, you need to send me an email from your UTD email to my UTD email. My office is in Founders Annex 2.402. One of the nice things, or at any way interesting things about campus, is that there's 3 buildings with the word Founders in their name, and we're in one of them. It's called Founders. Just north of here is another building called Founders North. And just west of here is another building called Founders Annex, or Founders West Annex. And I'm in the Annex. And the reason why I have to explain that is because, there's 3 buildings with Founders in their name. They all have a 2.402, and there's a math person in all of the 2.402s. So it can be quite confusing for someone who's looking for me, but isn't in the right building. Okay? Any question about that? All right. Good. So that's just concerning me and my office. My office hours are Monday and Friday, but no Wednesday. What was it? 11 to 12. And also Tuesday, Thursday, 10 to 11. Or by appointment. And I'd be happy to see you. Good. So concerning just technical details about various tools that we'll use. Among other things, like the UTD and just generally school policy, is I can't take your grades and just post them outside on my window. That's against the rules. In the same kind of way that your doctor can't just say, yeah, I left it outside your medical records. Just come pick it up. I can't do that. So as a result, there has to be a way for us to trade files with each other when those file contents have your academic records in them. And the way that we do that is with something called Box. Specifically, there's a website called box.com. And UTD has a contract with them, and that's the officially blessed mechanism for me to send you files that have your grades in them. So we'll be using that because you're a UTD student. You have a Box account. You may just have not understood this yet. So on Box, there's going to be several files. One of them is the syllabus. I'll send you a message soon on Box. When I share these files with you on Box, about half of you are going to get a message that says Brady McCary wants to share a file with you. That's me. You should click yes. But for reasons that I don't understand, the other half of you just aren't even going to get a message. So I'm going to send another message on e-learning that says, okay, go to this web page. And do it. Okay, so the syllabus will be here, as well as things like the notes. That is to say, these notes that I'm writing right now. I'll scan them and post them here. In addition to that, there will be your written homework will be posted here. So what that means is I'll post some PDFs and then send you a message and say, okay, there's a new homework. You go to Box, you download it, print it, you do the exercise, you bring it to lecture. And then after the graders have graded it, then I won't return to you those physical pages. Rather, I'll scan those pages and post them to Box. Okay? Any question about that mechanism? Okay. So Box is it's a neat thing. All right. Besides Box, we'll also be using something called GitHub. Okay, so let me explain the problem that we have to solve. Okay, so this is an introduction to programming class. So a program is like just a file. Okay, in the end, it's just a text file, and more or less, in the course of the semester, you're going to write maybe 50 short programs. So that's about 50 files. All right. Then there's about 100 of y'all, because I teach 2 sections. There's about 50 in this one, about 50 in another one. So that's 100 students and 50 files per student. So that's 5,000 files. Okay. Now here's the second matter, is that I have to keep track of 5,000. Y'all just have to keep track of 50, but I have to do 5,000. Here's another matter, is that when you submit a program to me, I'm going to grade it. Now, part of the grading is purely automatic, where basically I take the program that you've written, I provide it some inputs, and then I detect whether or not it produces the correct outputs. Okay, so that's a purely mechanical thing. I just tell the machine to do that. But part of the grading process cannot be automated because here's a good example. The absolute value function, right? We all know what that is. There's a multitude, in fact, a multitude of ways to implement the absolute value function. One of them is, you take the input and you check. Is the input negative? And if it's negative, then you negate the input, and that's the new output. So like, for example, the absolute value of -8 is -8. Okay, but another way to compute absolute value is to just take the input, whatever it may be, square it, and then compute the square root of that. That'll do it too. So concerning those two different techniques, both of them will produce the correct answer. But if I was to say, make an absolute value function that does it the one way, and then make another one that does it the other way, just by looking at inputs and outputs, I can't detect if you did it the way that was specified, you see? So I've got to look at it with my eyeballs. All right. So, I look at it. So part of the grading is mechanical, and part of it is, with the, the two aspects of the grading are called the silicon. I refer to them as the silicon aspect and the carbon one. Silicon meaning that we're having the machine do that, because microprocessors are made out of silicon, and the other one is carbon, because I'm the carbon computer, the one made out of meat as opposed to the one made out of silicon. Okay, so suppose you don't get a programming exercise correct. Okay, that's concerning, but in the end, the way we're going to do it is like this: is I'll post a message, and it'll say, this is not right for such and such reason. And then you look at that, think about it, and submit a correction, and then it gets graded again. And maybe you make some new and different errors, and then I tell you about it, and we just go back and forth until you have it right. Okay? So what that means is that there's not really 5,000 files. What that really means is that on average, if it takes like 8 attempts for you to get it right, that really means that there's 50 times 100 times 8 files. And that's like 40,000 files, and that's not reasonable. if you see what I mean, because when I'm grading your programs, I don't want to look just at the one I'm currently looking at. I want to see, okay, I'm looking at this student, this question, and this is the 7th version, and I want to see all of the previous versions too. You see what the problem is? Okay, so it almost sounds like unreasonable to even fathom how to solve this problem. Thankfully, this problem has been solved for a long time. One of the ways to solve it is with a program called Git, and then a particular web page, a website that manages Git is called GitHub. Okay, so that's what GitHub is. That's where we're going to share program files, and I'm going to send you, you'll submit a homework assignment, which has each homework assignment has on the order of like 20 different graded elements, and then every once in a while suddenly I'll send you like 17 emails that said graded element thus and such is not right. Suddenly like 17 messages all at the same time. So that's what GitHub is. Any question about what GitHub is? Okay. So this is for the management of program files. All right. So we'll be using Box. We'll be using GitHub. Is there any other specific stuff we'll be using that I need to mention? Not really. I mean, we'll be using e-learning also, but y'all know what that is. Any questions? All right. Let's see, what next? Box, GitHub. All right. So then, concerning the graded items in the course, there's two kinds of graded items. One of them is called PEX, which just means programming exercise. So we will have had a lecture over the relevant math topic introducing the math topic, and I'll also take the time to introduce any specific programming topic, programming idea that's necessary for you to comprehend the math topic. And then, I'll say, okay, there's a new programming assignment on GitHub. Okay, then you do it. Okay, good. Besides that, there's also WEX, which just means written exercise. So these are math exercises in the normal sense of math courses. So these are math exercises that you'll do, with pencil and paper. Concerning these written exercises, there's two varieties. So there's a homework WEX. These will be posted on Box, and I'll send you a message about that. These you'll download, print, complete, and turn in. The first, I can't remember, like 2 or 3 of the homework WEXs, they're not actually math exercises, they just contain instructions. Okay, but you should read those instructions carefully because they detail the way that such things are graded, the WEXs. Besides homework WEXs, these are the kind of thing that you do at home, homework. But there's also quiz WEXs. And these are things that you do in here. So just like homework WEXs, but in lecture. Where homework is concerned, I encourage you to utilize any resource that you can imagine. Work in groups, it's fine. But you need to understand that the university has an academic dishonesty policy, and it's expected that y'all can talk about the homework exercises, and that's fine, but your work needs to be your own. Okay? Now that's kind of hard to police, to be honest with you. So the way it gets policed in this class, and generally in all the rest of your classes too, is that I just give you a quiz that's basically very similar to the homework. And if you didn't do the homework, then you're not going to be able to do the quiz. Okay? Any question about that? All right. So concerning these, a subset of these two things will be graded out of 10. And the rest will be completion, worth 1 point. So I'm not going to get too much into these details because that's all. It's on among the written instructions on the first several WEX homeworks. So, but I want to be clear about the way this part will work. So some of them will be graded out of 10. So, for example, today. We're going to eventually get to some math, and I'm going to post some exercises, and you're going to have to download them, print them, complete them, and turn them in. You're going to bring them here to lecture, and maybe it'll be the case that I select one of them to be graded out of 10, and maybe furthermore you make like a 3 out of 10 on one of those. Okay, that's concerning to me. I don't want it to be that way, and neither do you. So after the out of 10 thing is graded, then I'll post a key, both PDF and video, PDF on Box, the video on YouTube, and you can look at the grader's remarks, you can look at the key, and be able to say like, okay, yeah, I see where I didn't understand it, and what was wrong or whatever. And then anything that's graded out of 10, I'm also going to give you a chance to redo. But I might announce the redo opportunity in advance, and I might not. So let's go with this hypothetical. Suppose that one of these that you turn in soon is graded out of 10, and you get 3 out of 10, and you think, oh no, I don't want that. Then I'll post the key. You look at the key. You look at the grader's remarks. You get familiar with the exercise, and then maybe like a week later, we're at the end of some lecture, and then I say, okay, now we're going to have a quiz, and it turns out it's a redo for the exercise that we're talking about. And if you don't want to redo it, if you don't want to make an attempt, you can go ahead and leave. But anybody else, you can stay. So if you choose to redo that one, then whatever it is that you get on the redo, that will now be your grade. So the policy is replacement, not whichever is better, but rather replacement. So that means that your grade could go from 3 out of 10 to 10 out of 10, but it could also go from 3 out of 10 to 1 out of 10. Okay. So the purpose for that policy basically is just my teaching philosophy, and that is that I'd like for you to be able to understand the topic at the time that I ask you about it, but maybe you don't. Okay, that's concerning, but all I really have to report to the school and the society at large is how you did by the end. So like if you didn't do so excellent in the middle, that can kind of just be between you and me. Okay? But that also, the door swings, it cuts both ways, because if I measure, I have to just report whatever I last measured, which is why your grade can go down. Okay? Any questions about that policy? Yeah?
Will all quiz X's replace homework X's, or is it just the ones you say that?
Anything that I select to be graded out of 10, there will be a redo. And to be clear, some WEXs can be graded out of 10, but some quizzes might be graded out of 10, but not all, and some homeworks might be graded out of 10, but not all. In particular, I do not announce in advance which ones are going to be graded out of 10, because that would bias your potentially bias the amount of time you spend on it. Okay, and all of the questions are important. I would grade them all out of 10, but then my boss would get upset because I'd be overburdening the graders. So I can't do that. Other questions? Okay. Finally, as far as the meetings, the meeting pattern for our course is Tuesday, Thursday, 11:30 to 12:45. On Tuesdays, with the exception of today, we will be in lab, and we'll be in the Brazos lab. In Founders. Now, as it happens, the Brazos lab is like right over there. So there's a computer lab that's right behind us. The one that and you can like see in there. That's not the Brazos lab. That's the Founders lab. So you go in there, and then at the back there's a door into a smaller room. That's the Brazos lab. Okay. So on Tuesdays we'll be doing that, and on Thursdays we'll be doing lecture in here. And then, the way the course will go is that, we basically alternate. Is that we lecture in here, I go over whatever math topic is going to be covered in the next programming assignments, and any new programming ideas I want to talk about here, and then we go to the programming thing. Because it's sort of Well, let's talk realistically here. So there's a large variety of experience in the room, and y'all might not realize it. So I want to make sure that y'all kind of understand the situation you find yourself in. So my experience is that about a third of you have written some programs before. Good. So if you're in that case, if you're in that situation that you know how to program in at least one programming language, then you're probably going to find the programming aspect of this course really straightforward. Another third of you haven't done a lot of programming, but maybe you know what it is and you just have barely done it. Okay, y'all will be okay. And then there's another third of y'all that basically have never done anything like programming. Okay, y'all are going to have trouble. It's going to be difficult because here's the deal: is that the computer. The reason why computers are so powerful is they do arithmetic extremely fast. So like much faster than we ever could, right? A human being. So like something little like your cell phone will do more additions and multiplications and things like that while you're watching a cat video on YouTube, okay, than you ever will in your whole life. In fact, probably all of us will ever do by hand in our whole life, which is one cat video. So they do arithmetic extremely fast, but so that's what makes them real powerful. But the other thing is that the computer is going to do exactly what you tell it to do, and that's both good and bad. And what happens is that you know, notice that I said the computer is going to do what you tell it to do. Okay, and I'd like you to contrast that with this other statement that's false. The computer is not going to do what you intend for it to do, because the computer has no idea what you intend. And it doesn't even know what intention is. In fact, it's completely nonsense to say that the computer knows anything. So what happens is that when students are learning how to program for the first time, a lot of students find it extremely frustrating, because basically they say, the computer is not doing what I tell it to do. And no, I'm sorry, the computer is in fact doing exactly what you told it to do. What you mean is that the computer is not doing what you intend for it to do, and the actual fact is that you're not telling it you're not telling it the right thing to do. You only think you are. So the real problem, the real suffering that students have to go through is that you've got to get over the idea that you speak clearly. And think clearly, because you might not speak and think as clearly as you imagine. Okay, so I'm telling you that for a variety of reasons. One reason is that you know, if you can make it through a programming course, and maybe even especially a programming course about mathematics, that can really change the way that you think about problems and putting all the steps in order and things like that. So that's good. But you also need to understand, for anyone that I'm talking to that's never done a written programs before, a third of the class has. Okay, and you're going to watch them. You're going to see them basically just breeze through these programming exercises. You know, and you won't be. Don't try not to take that to heart. You know, try not to take that to heart, because probably what that means is that you just have never really written any programs, and the person you happen to be looking at the time has. Okay, so you know, to put an analogy on it, you know, I don't speak any like Russian, you know, except for like a couple words, and you know, if I had a buddy who's not a Russian, but they took a bunch of classes in Russian, and then we went to Moscow. And then they're able to get it figured out, but I can't. You know, I shouldn't feel real bad about that. I mean, they took a bunch of Russian courses. You see what I mean? Okay, so I'm just telling you that because this is not the first time I've taught this course, and I see students. Some subset of students have a bad time if I don't explain that point real clearly at the beginning. So any questions about that? Okay. So as a result of that and other matters, that's why we're going to do half lecture and half lab. So the point is that in later programming classes, you could probably get away with having basically no labs, but for a first programming class, you can't really do it. In the sense that, you know, I could like, you know, if this was a class about digging ditches, you know, in the dirt, then, you know, I could talk about it a little bit, but I think we can all probably agree that I could get a lot done if we would just go out into the field with a shovel, you know, and just say like, you know, this is what I'm talking about, rather than talking abstractly about shovels and dirt. So we're going to go into the lab, and you're going to write programs, and I'll be there, and you can you can ask me questions. Good. Any questions about the way the course will go? Finally, concerning the programming exercises, you can, like I said, you know, you'll make a submission, and then it'll get graded. I'll make comments, and then you can make corrections. It'll get graded again. But that's going to have its limits. Okay, what I mean is that I'll keep track of the last time you made a submission for a particular exercise, and I'll inform you, you know, what the window is, and you know, if you just wait for a long time, I'll just say, sorry, I'm not. You can't turn in any more corrections to that one. You waited too long. Okay, and you know, I won't. It won't be okay for you to like, you know, make like a one character modification to the file just so you can make the window bigger. You know, that's not going to work either. Okay, so basically, I'll let you do as many corrections to your programming exercises so long as a reasonable person would say, yes, they are really trying to do this. But you know, if you're just trying to game it and just wait to the last second, I'll just cut you off, and that'll be done for that assignment. Okay. Was there anything else that I wanted to say? Yeah, there was something, but it's slipped my mind. It'll come back. Any questions? Okay. Well, there really was something, but it's gone. That's in the syllabus. Oh, I almost had it.
So, how often are the quizzes in the
I'm gonna try and make it basically every lecture. The reason is because you know, and furthermore, the rule will be that you can't turn in homeworks except in lecture or lab when they're due, and you can't take quizzes except in lecture or lab when they're given, and that has the well. The reason for that is that it encourages attendance and participation. Other questions? Man, it's right on the edge of my thought. It'll come to me later. Okay, so to that end, let's learn how to sort of speak precisely. Okay, we're going to work on simple problems that we all know, we're all familiar with, but to some extent and to some degree, writing a program is like explaining something to an alien child, you know, that doesn't know our ways. So you've got to be extremely precise about what you say. So let's get a little bit of language out of the way. So in the first place, we have naturals, the set of naturals. is denoted with a bold N. So that's an N, and then it's one of its legs is a box. But the only reason for that is that's the stylistic convention to signify that something is bold. Because I don't have a bold pencil. So that just means bold. The naturals are the set 0, 1, 2, 3, etc. And before anybody comments or sends me a hate mail, I'll just mention anytime you talk to a mathematician or a computer scientist and they're talking about the naturals, you need to very carefully ask them whether or not they consider 0 to be a natural. Okay, because it's very easy to go find a math textbook where the naturals start at 1. But for every one of those, you can find another textbook where the naturals start with 0. So in our class, the naturals start with 0, and you always need to check whenever you're talking to one. Okay, but yeah, so I'm like on team 0. 0 is a natural, and all the rest of everybody else is just a heathen if they think otherwise. Not really, I don't think that. Okay, so the naturals. The next set that we need to know by name, the integers. Okay, so if the naturals are denoted with an N, then what are the integers denoted with? A Z, obviously, right? Now, does anybody know why it's a Z? That's more obscure. That's right. Is that when this was being set down, it was being set down in a German-speaking country, and the German word for there is a German word, Zahlen, which means number, and that it starts with a Z, and in German, Z is pronounced approximately like TS, which is why it's Mozart and not Mozart, right? So Z, 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. So the integers. The next bigger set that we're going to single out by name are the rationals. The rationals are denoted with Q. So the rationals are the set of all P divided by Q such that P and Q are in the integers and Q is not 0. So in case you're seeing this kind of notation for the first time, this vertical bar is pronounced, in English anyway, as such that and that symbol is pronounced in, as in inside, or is an element of. Okay, so what's, just to make sure. Okay, yeah, that's another thing I wanted to say, is that the prerequisite for this course is pre-calculus. Okay, so then I completely understand that many of you have taken calculus, and maybe even like calculus 1, 2, and 3, and whatever. But at any rate, the prerequisite for this course is pre-calculus, which means I can't assume calculus. Fine. So just in case, I want to ask, can someone give us an example of a rational? 2/3. Okay, because, well, 2's an integer, 3's an integer, so 2/3 is a rational. All right, good. What about the number 2370? Is that rational? But then it doesn't look to me like it's the ratio of two integers. Okay, divide by 1, good. And then is 2370 over 1 the only conceivable way to represent it? No, right, because you could, very good, you could multiply the numerator and the denominator by 2 and a bunch of other stuff. Good. Can someone give us a number that's not rational? Pi. Okay, good. E. Okay, so then pi and E. How about another one that's not so complicated? Oh, besides tau. Come on now. Square root of 2. Okay. In fact, the square root of any prime is not rational. Okay. So these things, these are not in the rationals. So that brings up a joke, right? So concerning primes, 2 is prime. Sometimes math majors can get to like the sophomore level and not have realized that 2 is prime, but of course it is, because a prime is just a natural, a positive natural that's more than 1, and its only factors are itself and 1. So yeah, 2 is a prime. But that's the subject of a funny joke. In a lot of math theorems concerning number theory, you have the phrase called odd prime, which just means any prime except 2. That's what that means. And so the joke is that 2 is not an odd prime. It's the oddest prime. Because 2 shows up in all kinds of places that are strange. Okay, so then because of this, the rationals have a lot of gaps. And because this is, the only thing I can assume that is pre-calculus, I'll just write gaps in scare quotes. It's missing pi. It's missing the natural number. It's missing a lot of things, actually. So there's a lot of other sets to talk about, but we're gonna skip to this one. And what I want is the smallest set that contains the rationals, but doesn't have any gaps. What's its name? The reals. It's noted with R there, and I can't be really super precise about what that means, but I'll just say it's the smallest set that is like the quotients, and it contains, like the rationals. It contains the rationals, but it has no gaps. Scare quote gaps. Yes? So there's a lot of questions, okay, that basically I can't get into, but I'll answer your question with a question. Can you think of any sets that contain the reals as a proper subset? The complex numbers, for example, right? So that because the reals are contained inside of the complex numbers, that means that the complex numbers, even though they don't have gaps, it's not the smallest set. So I'm just going to have to leave it there. So you get into the idea of what this smallest means. So I guess I'll put scare quotes around smallest also, because that means something specific. You get into the specifics, the nitty-gritty of what this means, usually in a senior level analysis course, but we're not going to talk about it here. No gaps, good. So also, I want to make sure that you understand that the name reals is actually a joke. and every time I say reals, I laugh a little bit. So now I want to explain to you why it's a joke. So here's the deal: is that one of the things that you study in undergraduate math is you want to study polynomials, right? Mainly because they're just real easy to deal with. Because polynomials, just to evaluate any polynomial, just requires a very short list of adds and multiplies and subtractions to evaluate it. So concerning, like, say, this equation, x squared minus 9, right? That's a polynomial, right? And then we want to ask, can we solve an equation involving this and say equal to 0, and then you learn how to deal with this, and then the left-hand side factors to x plus 3 multiply x minus 3. So this is negative. The solutions are x is negative 3 or x is positive 3. So that's nice. So you learn how to solve polynomial equations. Then here's a polynomial. No one can dispute that it's a polynomial. But then you ask, can you solve this one? And the answer is, well, to some extent, it depends on what you mean. But if the question is there a real x that you can plug into this equation and the result will be true? The answer is no. So there's no real x. That solves that equation. Now, like back in the day, there was Newton. He's the famous guy. Calculus, and Leibniz. That's the other one. Physics people and math people alike like to claim him. Because he's so awesome. But the actual truth is that Newton was not a mathematician or a physicist, mainly because those words didn't even exist at that time. Okay, that wasn't even a thing. So, if you look at it, what he was is at the time the name for it was a natural philosopher. So that's what those folks were. The dividing technical people into mathematician, science, engineering, whatever. That's a relatively modern thing. So it came to pass that people, natural philosopher types, were considering this equation, and the ones who basically would be engineers and physicists and things like that just said, there's no solution. And the ones who eventually would be math types said, we're kind of like, well, what would it be like if there was a solution? What would it be like? We'd have to have something that when you square it, you get -1. And the people who eventually would be, engineering types basically said, well, sort of facetiously, that's just that's in your imagination, And so, as a result, basically, they ended up naming that the imaginary number, because the imaginary unit is the thing that squares to -1, well, and the negative imaginary unit. So the set of numbers that includes, among other things, the imaginary units is what? Complex. And in this case, complex doesn't mean, let's write this down. So the complex numbers, these are the set of all expressions of the form a plus b multiplied by I, such that a and b are real. And I has the interesting property that when you square it, you get -1. And then you take an algebra course or whatever, and you make several interesting realizations about it. In particular, I can't possibly be a real number, for example. So these are called the complex numbers. Not, and in English, the word complex has two meanings. One of them is means like difficult, and the other one, but there's another meaning of the word complex. So an example of its usage is in the phrase shopping complex. So a shopping complex is not a region of the earth in which it is particularly difficult to shop, right? That's not what that means. Rather, that just means that it's a region in which there are a multitude of places to shop. So complex in this case means just having multiple parts, a real part and an imaginary part. Good. So, you know, the would-be physicist science folks called this the imaginary numbers, you know, that one. And then the math folks, you know, responded in kind by calling these the reals, whereas formerly they were just called numbers. You know. And then, you know, as history would have it, the mathematicians got the last laugh. The reason why is that the crown jewel of all of science and physical theories is quantum mechanics, especially something as wonderful as quantum electrodynamics. And what number system do they use? Complex numbers. You did it to yourself, you physics folks. Haha. So every time you hear reals, it's now you understand the joke if you didn't get it before. So what we're going to do is I'm going to use those definitions and symbols from now on without comment or apology. So now let's get some practice defining things very, very carefully. So for example, let's define multiplication of a natural and a real. So I'll say let n be natural and x real, and I'll say that assume we know how to add. In the reals. But we don't know how to multiply in the reals. So we don't know how to do that. Okay. So specifically, we're going to try and figure out how can you multiply a natural and a real. Make a suitable definition for it. Okay. So 2 multiply x. Okay. 2 multiply x. So 2 is a natural and x is a real. What this means, the way we're going to define it, is that we're going to make 2 copies of x. We're going to make 2 copies of x, and what we're going to do is we're going to add them. You know, because we already know how to add. So here we have it. Now we can do 2 times x. Okay. So how are we going to do 3 times x?
3 sounds good.
Yeah, okay. So now we make we make 3 copies of x, and then we'll add them. Okay. So you can imagine I could keep going, right? 4 times x. Okay. So 2 times x means make 2 copies of x and add them all up. 3 times x means make 3 copies of x and add them all up. What about 1 times x? Now the phraseology gets a little bit clumsy. So this would I guess you'd have to say it like make 1 copy of x and add them all up. Okay. But you know, now we come to the problem. Now we come to like the place where it's not exactly clear how to make it work. So what's the least natural? 0. So we need to know how to do 0 times x. Okay, now let's think about this and let's observe the problem. So the problem is that we said, okay, 2 times x, that means make 2 copies of x and add them all up. And then 1 times x means make 1 copy of x and add them all up. So 0 times x is what?
Add up 0 copies of X.
Right, but you know, what am I supposed to write? You know, it's like, okay, I've produced 0 copies of x. Can you see that there's like an issue? This is the kind of thing where the computer says, you know, it just blows up. You know, it just says, well, this is what you told me to do. Okay, so in fact, there's just something wrong with the definition. In fact, we need to modify it. So now, as far as you know, like the course is concerned, notice that I was pretty carefully lined up all the stuff. You know, everything's like in nice little columns there. But do you also notice that the amount of horizontal space on either side of the equals is asymmetric? Yeah, that's not my style. So anytime you see me doing that, now you know that there's a punchline coming. So I left some space to fix something. So we all know what 0 times x is really supposed to be. What is it? Should be 0, right? So in fact, the correct definition of all of this is that there's a 0 here. So the correct definition of 4 times x is that you take a 0, you take 4 copies of x, and you add them all up. And that works for any natural. So generally speaking, the definition of n multiplied by x is 0 plus, and then x plus dot 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 plus x. So there's n of these x's. Okay, neat. Any question about that? It's fine? So now we're going to do the next one very fast. Oh, are we done? No. No, 45. Okay. So now let's do it again. Let's say let n be natural and x in the reals. Assume we know how to multiply in the reals. Okay, so for this one, because we knew how to add in the reals, that made it immediately possible for us to define multiply, but only if the left operand was natural. So what does this allow us to do? If we know how to multiply, what do we know how to do? The next thing. So what I mean is that add gives you repeated addition, gives you multiply. What is repeated multiplication? Exponentiation, right? Or not really that, but rather exponent, right? Raising something to an exponent. So okay. So in particular, x squared. Okay. Well, that means make 2 copies of x. And what are we supposed to do with them? Add them? No, we multiply them, right? Okay. And then x cubed. Well, that must mean make 3 copies of x and multiply them. Right? Okay. So then x to 1, that means make 1 copy of x and multiply them all together. Okay, and then here's the place where it gets things go off the rails a little bit. Then remember the least natural is 0, so then we need to define x to 0, and you know, what's that going to be? Okay, now you're just playing with me. I thought it was 0 last time. Last time when when I did the exact same game and I left myself this space here, I put in a 0, and now you're telling me 1? This is too good to be true. I don't understand. Why 1? Why not like 7? Why 1? Why 0? Yeah? Okay, very good. So 0 is the identity of addition. You want, what that means is that where addition is concerned, what we want is we want an element such that adding with this element is the same as doing nothing, right? So like x plus 0 is x for all x. As a result, 0 is referred to as the additive identity. Okay, so then the question here is why should it be 1? 1 is the multiplicative identity. That's the reason. If we had some other operation, instead of add or multiply, if we were banana-ing, then we'd need the banana identity, whatever that is, right? So can you see what goes in that spot? So there's a 1 here. 1, 1, 1, 1. Of course, there's a little, I have to put a little asterisk here because this is a math class, because this is almost correct. What's not right about this? Well, no, I'm not saying that there's a multiply. I'm putting a note here. I don't mean multiply. So there's one little problem. There you go. For x not equal to 0. Because remember, 0 to exponent 0 is undefined. Okay, good. Any questions so far? All right. So, now, concerning, that's interesting stuff concerning numbers. But there's other things that are interesting in math. For example, let's write this down. Because I could say something like let f be a function from the reals to the reals, and let g be a function from the reals to the reals. So all that means is like the kind of function you might talk about in pre-calculus, like like sine of x, something like that. Okay, you put a real number in, and then out comes a real number. So to make sure that you understand what I'm requesting of you, I want to kind of give you a visual model. So I'd like for you to think of a function like a machine. So like here's a machine, an F machine. You put an F in. You put an X into the F machine, and then you hear it whir and buzz and all kinds of stuff, and then out comes the output, and the name that we give to the output is f of x. And we've got a G machine that does that too. It does its thing. Okay, so then just like you can take two numbers and add them together and get another number, or multiply them and get another number, you can take two functions and add them and get another function. Bear in mind that I'm sort of like avoiding the whole issue of like domain, but I'm just setting that aside. So we could define, for example, a new function which we'll call f plus g, and the way that we'll define it is pointwise. What we'll do is we'll say, if you've got something called f plus g, what happens when you plug in an x? Okay, so we'll define this by f plus g, and when you plug in an x, what are you supposed to do? Yeah, you evaluate the function on the left, you evaluate the function on the right, and now that I evaluated both of them, what am I supposed to do with the outputs? Yeah, you add the outputs together now. But what I'd like for you to observe is that concerning this process, you could have done it in principle in either order. You could have done You could have done f first, and then g, and then added them, or you could have done it the other way. So sort of diagrammatically, you might make it look like this. So you give an x to some big machine now, so it's big, because it's got to contain two functions, two littler functions. Out comes f of x there, and like this one, g of x, and then now you take those two, and by the time they come out, what you observe is this. And the name of this box is f plus g. There's nothing magic about plus. I could have written minus or multiply or divide, and it would be all exactly the same. But concerning add, subtract, multiply, and divide, you can do all that with numbers. But there's something you can do with functions that you can't do with numbers. What is it that's like this that you can do with functions but not numbers? Yeah, you can compose them, right? You can compose them. So we'll define f, and then the composition operator is written as a circle. F compose g. We'll define a new function, f composed with g, and we'll do it like this. If you want to take the f composed with g function and evaluate it at an x, what is it you're supposed to do? Well, it's f of g of x. Now, that's something that you can make it through high school and just and know that, but you can kind of lose track of what that really means. What that means is that concerning this diagram, if this was like some kind of process, and there were two people, maybe the F person, they could finish first. Maybe they're fast, and then the G person's not as fast. But the whole thing has to wait until both people are done, right? But in principle, both of those folks can do it at the same time. Composition's not that way. Rather, the process looks like this. You say X has to be given to who gets the input first? G gets it, right? G gets an input, and then out comes a G of X. And then what do you do with that G of X? Now you got to give that to F. So F can't even get going until G's done their thing. So if you put all of this in a box right there, that's the composition there. So you can't do F and G at the same time. You got to wait for G. And then in real life, the way this raises its head is like in an assembly line. That's what this is. In the end, that's the reason why functions are what we talk about all the time in math. Because you learn, like, Henry Ford is famous for what? Because Ford Motor Company is the first heavy manufacturing industry where the assembly line was used. That's the reason. That's Henry Ford's claim to fame. So that's also the reason why, more or less, a high-level reason why functions are what we study in math instead of what else. So all right. Now that I can be sure that you know what composition is, I can ask. I can say, okay, let's define the following. Let's define f with n superscript on natural n and f, which is real to real. So now we've got instead of a natural and a real, instead of an n and an x, now we've got an n and an f. All right. So we'll do it like this. So if f squared, so because f is a function, I don't mean repeated multiply. What do I mean? I mean repeated composition now. So this would be F compose F. Okay, and then F cubed, like that. Well, that would be make 3 copies of F and compose them all together. Yeah. All right. You see the punchline coming, I hope. So then F to 1, that'd mean just F, right? And then the question is okay, what's F to 0 then? Ah, okay. So can you see that that there's got to be identity something, right? So you need to be a little bit careful about language. So it's not. I would encourage you not to call it the identity function. Okay, rather a better name, for example, is that 0 is the additive identity. It's the additive identity because when you add 0, that's the same as doing nothing. 1 is the multiplicative identity because when you multiply by 1, that's the same as doing nothing. So because we're talking about repeated composition, probably the right name for the thing we're looking for is the compositional identity. That's what we want. We want a function. That's the kind of thing we're looking for, and we want it to be. We want it to have the property that composing with this function is the same as doing nothing. And we're out of time, so I want you to think about that and be ready to answer that on Thursday. What's going to be the compositional identity? Okay, so have a nice Tuesday.